Hello again. So in this video we're going to be exploring how to calculate the pH of a weak acid. So the pH of weak acid is different than taking the pH of a strong acid, because strong acid dissociate completely 100%, almost 100% of the water. So just like take the negative logarithmic of the initial concentration of the strong acid. But in this case we're not doing the same thing. We need to do an ice table to calculate the pH of the weak acid. So here we go. So in this case we are having an acetic acid. So if you don't know acetic acid formula, you should familiarize yourself with it. So acetic acid formula is CH3COOH. So let's write this down. So acetic acid formula is C3CH3COOH. And this acid is in equilibrium, so it dissociates to CH3COO minus, and the extra H here, it goes to water, so you get H3O plus, or you can write it as H plus, which is the hydronium ion. Okay, so now we're gonna construct the ice table. So the ice table, of course, you're gonna have an initial concentration, which is I, C for change, and E for equilibrium. So when everything is equal to each other. And you have three species: the acetic acid CH3COOH, which is your reactant, your product, acetate, or the conjugate. We call it the conjugate base of the acid. So it's CH3COO minus, and your hydronium, you can just write H plus. So the initial concentration of your acetic acid is given in the equation here. So it's 0.1 molarity, and everything here is measured in molarity. And here you start with 0 because you just dump the acid. We assume you just dump the acid in the water. So the change will be, we don't know the change because that's what we are going for or after. So you have 0.1 minus x, and you have plus x for your products. And remember, it's 1-to-1 mole ratio, so everything will be x. So about that, and your final. So just to not confuse somebody here, we can just like erase the 0.1, because some people say like that should be the final. Yeah, but the change is still minus x. So yeah, you could say so. So your final will be 0.1 minus x, and 0 plus x is just x, and 0 plus x is just x. So we just constructed the acetic acid ice table, and now we're gonna solve for the x's, which is your final concentration. So to solve that, we need to use the Ka, which is given in the equation as well, 1.75 times 10 minus 5, the association constant, or the this Ka. Some people use Kd for it, but it's the initial the rate at which CH3COOH, which is acetic acid, convert to acetate. So how you do that? So the simple equation, Ka equals the products the concentration of the products, which is CH3COO minus, times your hydronium ion concentration divided by your concentration of the reactant, which is CH3COOH. So we know that the CH3COO minus final concentration is just an X. And same thing for the hydronium, it's just an X. And for CH3COOH, which is acetic acid, is going to be 0.1 minus X. And we're going to assume that the X, since your K is slightly, I mean, it's not that big, but it's not that small as well. And 0.1 is also big enough to diminish the effect of the X itself. So we're just gonna, let me just change the color. 1 second. So we're gonna cancel out the minus X and assume by approximation that minus X is very small compared to 0.1, so we don't have to struggle with the quadratic formula. So after that, let me just add a new page. Or let me just finish this here first. So let me go back to draw and use the yellow pen. So x times x is just x squared. So you remember, when you multiply the same bases, you add the exponent, and each one has exponent of 1. So you add 1 plus 1 equals 2, and you have the x divided by 0.1 equals to the Ka, which is 1.75 times 10 to the minus 5. And that should end up you giving. So now how you solve that? So you know, of course, multiplication. So you have to, in order to solve for x squared, you have to multiply both sides by 0.1. So when you apply both sides by 0.1, you get 1.75. We got my calculator. To the power of minus 5 times 0.1. Should give us 1.75 to the power of times 10 to the power minus 6. So you end up with getting this value, 1.75 times 10 to the negative 6 equals x squared. So for that, take the square root of both sides. Oops. Just get back. And here we go. So x is going to be in the positive and negative value, but remember, you can't have negative concentration, so you just ignore the negative value. So you end up with the square root of the answer, and that should give you a value close to 1.32 times 10 to the minus 3, and that's in molarity, because we start with molarity here. As you can see, we end up with molarity. So that's how you find the value of x. Now we're after pH, and remember, pH is just nothing but the negative log of the hydronium ion, and we know the hydronium ion at equilibrium is x, and x is 1.232 times 10 to the minus 3 molarity. So just like clear out the board now. Oops. No, we don't clear out the question. So we just get back here. Choose the. I just do this. Okay, here you go. So we know that x equals, or we start with H plus, which is the hydronium ion, equals X, and X equals 1.32 times 10 to the minus, what was it? Yeah, minus 3 molarity. The pH will be minus logarithmic of 1.32 times 10 to the minus 3 molarity, and that should give us, so we end up negative logarithmic 1.32 times 10 to the minus 3, and that should give us a value close to 2.88 pH. So it's pretty good acid in terms of strength, and so that's how we calculate any pH for any weak acid. So thank you, and see you in the next video.